So, we are going to start a new topic today. We are going to discuss semi-classical approximation. This is also known as the WKB approximation. This name WKB basically came from the names of the persons who actually first proposed this method. W stands for Wenzel, K for Kremers, and B for Brillouin. And this was proposed by these three people in the year 1926, when it was the formative years of quantum mechanics. But it turned out that before them, Jeffreys, a mathematician, actually did the same calculation, but that did not get much popularity, and it got popularity also when in quantum mechanics this method was applied. Of course, they did it independently, WK and B. So in some books you might find the same method being termed as JWKB approximation. So what does this WKB approximation tells us? It actually provides some approximate solutions for differential equations with coefficients are changing slowly with spatial variation. So the approximation is termed as semi-classical. It's because when applied to quantum mechanics, we have the quantum mechanical wave function, but classical physics illuminates the main features of the quantum wave function. That is why this name semi-classical approximation is important. So it's not purely classical, not purely quantum, it's something in between. So what does one do in this semi-classical approximation? It all has to do with the de Broglie wavelength of a particle. In fact, the de Broglie wavelength of a particle actually can help us to figure out if classical physics is relevant to a particular scenario. And if you remember, the de Broglie wavelength lambda was defined as h, the Planck's constant, by p, the momentum of the particle. Now, it is very well known to all of you, you have encountered this de Broglie wavelength in your PH 101 course, also in PH 204 course, and it tells you that classical physics can provide very useful physics or physical output when your de Broglie wavelength is much smaller than the relevant length scale in the problem that is given to you. For example, if you have an electron and you are putting it via a slit, if the slit width or the aperture is much greater compared to the de Broglie wavelength, or lambda is much smaller than the slit width, then electron behaves as a classical particle. It goes straight and falls onto the screen. But if your de Broglie wavelength is comparable to the aperture of the slit, then the quantum effect comes in and you have this diffraction pattern on the screen. So now you can also think of this particular scenario in this manner. You can take the Planck constant h going to zero limit, and this will basically formally make the de Broglie wavelength very small. Or lambda, the de Broglie wavelength, will then be smaller than or equivalent to the length scale that is there in the problem. So what I said is that classical physics dominates if your lambda is much less than the length scale that is there in the problem, the relevant length scale. For example, if you think of this electron going through a slit, then if your de Broglie wavelength of the electron is much smaller than the slit width, then you will get some classical result. However, lambda comparable to L will give you some quantum aspect. Now, we all know that this H, or the Planck constant, is basically a constant of nature, and therefore we cannot really make H slash or H going to 0. So when I say that we are taking this limit H going to 0, then you think of this as you are doing a thought experiment in which we imagine some other universes or worlds in which H can take smaller and smaller values, making the classical physics more and more applicable. So that is some kind of a scenario that is possible. But if you want to look at from the mathematical point of view, then it's just the fact that H going to 0 makes your lambda smaller and smaller, and thereby at some point this lambda will become relevant or equivalent to the length scale that is there in the particular physical problem that you are trying to solve, and thereby your quantum effects might come out. So that therefore means that the semi-classical approximation that we are going to study will be applicable if a suitable generalization of the de Broglie wavelength is possible. That means if I can make this H to be small, and thereby this lambda will be slowly varying. So the semi-classical approximation basically will be set up mathematically by thinking of H slash or H bar as a parameter that can be taken to be as small as we would like to be. So that is the important point in the semi-classical approximation scheme. So let me write this, that semi-classical approximation can be applied or set up, and of course this is done mathematically by viewing the Planck constant as a parameter which can be as small as we want it to be. So first thing that we remember here is that when you first encountered the de Broglie wavelength, de Broglie first introduced this de Broglie wavelength in the context of a free particle, where you have a fixed momentum of a particle, free particle having the fixed momentum. But here we are looking into a slightly different version of the de Broglie wavelength. Suppose now we are actually looking at a particular one-dimensional problem where we have a potential which we have denoted by V of x, and the particle has some energy E, and therefore this particle in classical physics, E minus V of x is the kinetic energy of the particle. So E minus V of x will give me the kinetic energy of the particle at x. And of course, because my potential depends on V, the kinetic energy therefore, the potential depends on X, therefore the kinetic energy also depends on the position of the particle. Hence, we can write that P square by 2m should be equal to E minus V of x, or we can write P square as 2m into E minus V of x. There are two important points that I need to mention. First, when I say that I am using this h as a parameter, then it makes our life a little bit difficult, simply because so far, remember in perturbation theory, when you introduce that small parameter lambda, that lambda was a dimensionless quantity. That means when we wrote down, so this is an aside, when we wrote down the total Hamiltonian as h naught plus lambda h1, where h naught was the known Hamiltonian, unperturbed Hamiltonian, and h1 was the perturbed Hamiltonian. Lambda was introduced to keep track of order in the problem, and this lambda was a dimensionless quantity. But now, when we are viewing h as a parameter in the theory, remember h is no longer a dimensionless quantity. H has the dimension of angular momentum. So we are dealing with something tricky that we need to understand very carefully. So we have done two things which a priori you will say that we are not allowed to do in principle. For example, one is that we have taken the fundamental constant to be varying, or that means that you can take h tending to the zero limit, and secondly, we are trying to view this small parameter h, whereas this small parameter h has some dimension. It is not dimensionless, unlike your perturbation theory problem. So this is the subtle difference between this semi-classical approximation and the approximation methods that we have used so far. Now, let me come back to this point, that we had written down this expression of p square as 2m into e minus v of x. That means my p therefore depends on x. So this is some kind of a momentum which is dependent on the position. And this momentum is the momentum of the classical particle when it is located at some point x. Suppose we are looking at a particular point x, the momentum of the particle there is p at x. So therefore, we can define a de Broglie wavelength which depends on the position dependent momentum. So this lambda I can define now in this particular scenario as h by p of x. That means my lambda, the de Broglie wavelength here, is dependent on the position. So if I write it in terms of h slash, then this is 2 pi h slash by p of x. So now let us write down the time independent Schrodinger equation. So the time independent Schrodinger equation it is minus h slash square by twice m, where m is the particle's mass, del 2 del x2 psi of x is equal to e minus v of x psi of x. So this can also be written as minus h slash square del 2 del x2 psi of x is equal to 2m e minus v of x psi of x. But what is this object 2m e minus v of x? This is nothing but my p square of x. So this is p square of x psi of x. But we also know what this object is. This object is nothing but minus I h bar del x whole square psi of x, which is again nothing but the momentum operator in the position basis. So this we can write as p operator squared psi of x is equal to p square x psi of x. A nice equation that we have arrived at by doing this, where we know that this is an operator. To distinguish from this p, let me put this hat on top of this p, which denotes that this p on the left hand side is an operator, while on the right hand side we have p square as a function of x. So this equation looks like very close to be an eigenvalue equation, but it is not exactly an eigenvalue equation. The action of the momentum operator on the wave function is not really proportional to the wave function on the right hand side. Rather, it is the wave function multiplied by the classical position dependent momentum squared, which is this object, which of course is a function, it's not a number. Therefore, although at the first sight you might be tempted to say that this equation is an eigenvalue equation, but it is not. This is not an eigenvalue equation. So let me write it clearly that this is not an eigenvalue equation, because this quantity on the right hand side is not a number. So therefore, this is not an eigenvalue equation. Now we also know that there are two different regimes in this plot. If I look at this plot of Vx, where the particle is moving with a particular energy, there are two different regions. One we prefer to call the classically allowed region. Classically allowed region. The classically allowed region will always have the E energy greater than the potential, and therefore this will always imply, if you look at this expression, that if E is greater than V of x, then P square will always be positive. P square will always be positive. We can therefore write P square of x should be equal to 2m times E minus V of x, which is sometimes, if you remember, written as h bar square k square of x. You also have something called the classically forbidden region. The classically forbidden region should be some place where your E is less than V. So classically forbidden region, we will call this when P square x is negative, That means E is less than V of x. That means minus p square of x is 2m into V of x minus E. And if you follow the notation of Griffiths, then this is h bar square kappa square. So k in this equation was the real wave number. K was the real wave number, which of course is position dependent. And here this quantity kappa is also real because we have chosen this p square with a minus sign, but let us differentiate between this k and kappa. Now, the wave function that is generally being used in the WKB approximation are mostly expressed in the following form. So, the wave function which is used in WKB approximation, or rather JWKB approximation, is often expressed in polar form. What does that mean? You remember any complex number you can write as z as r e to the power I theta, where r was the magnitude and theta was the phase of this complex number z. So here also we can write the wave function in this manner. So capital psi x of t, function of x and t, as square root rho exponential I by h slash s x t. Let me write in the three-dimensional way. So I will explain what these quantities are. We are using first of all the three-dimensional notation for the most general case. Now these functions rho of xt and s of xt, these two functions are real. The function rho also is non-negative, and the function s has the dimension of angular momentum, because you know that the exponential function, exponential is always some dimension less quantity should be sitting here. So since we have this h bar in the denominator, s should also be of the same dimension of h bar in order to make this quantity within the bracket dimensionless. So s must be having the dimension of h bar, and dimension of h bar you all know is basically nothing but the angular momentum. So this s, whatever it is, has the dimension of angular momentum or h bar. So apart from being real, we have these following two observations about rho and s. That is, this is positive because this is within the square root, and s of xt has the dimension of h bar, that is angular momentum. I mean, if you look at this rho, using the symbol rho is justified simply because it is the probability density. Because if you calculate psi star xt with psi xt, then what you get is rho xt. So this is nothing but mod of psi xt squared. So this is clearly the probability density. So if this is probability density, then of course we can calculate the probability current in this scenario, because that's what we have already done in PH 204, that I have the probability density and I can calculate the probability current from that probability density. So if I calculate the probability density, what comes out of this calculation? Let us see that. So first of all, if you remember, just recall the formula for the probability current. It was H slash by M imaginary psi star gradient of psi. So if we calculate gradient of psi, so what happens is we look at the expression of psi. When gradient operator acts on psi, it gives us half from the square root, and then 1 by square root of rho xt, and then of course del rho of xt times the phase factor, which is e to the power I by h slash s xt. Then in the second term, when gradient operates on this exponential part, what do I get is this I by h slash, and then we will have the gradient operator on the function s of xt, and whatever remains should be rho square root rho xt times exponential I by h slash into s. So this is nothing but your psi of xt. So if we calculate psi star of grad psi into grad psi, then this will give me half, and then we will have gradient of rho xt, and psi star will have 1 square root rho xt, which will cancel with this rho xt, and the phase factor will have e to the minus is by h slash, so that will cancel this one. So the first term will simply be half of gradient, half into gradient of rho plus I by h slash, gradient of s was already there, and then we will have psi star psi. So psi star psi, as we have already seen here, is rho of xt. So this is rho of xt. That's it. So if you take the imaginary part of psi star grad psi, then it is going to give you 1 by h slash rho of xt gradient of s xt. So From this expression, if you compare with this formula, we will get J as rho del S divided by M. So it's basically a very nice formula that we have obtained. So this formula implies that the probability current J, so this is the probability current J, basically will be perpendicular to the surfaces of constant S. Probability current will be perpendicular to the surfaces of constant S. Why? So suppose we have constant S surfaces. We have different surfaces with S constant. These are different surfaces with different phase. But then we have this gradient of S. So the current therefore will be perpendicular. That we have already seen in our PH 102 courses. So these are the perpendicular functions. Now in classical mechanics or in classical physics, we know that a fluid with density rho which moves with the velocity v has a current density rho times v, right? So analogy with fluid mechanics, we know that J should be equal to rho times v. If we have a fluid with density rho which moves with the velocity v, then it has a current density which is rho times v, which is nothing but rho p by m. Now if we compare this with this equation, then we can get P of x to be proportional to gradient of S. For basic WKB solutions, we will see that the gradient of S is indeed the classical local momentum, but we have used this kind of approximation sign simply because this is an association that is not generally valid. So if we consider one example of the free particle, if we consider this free particle, we know what psi of xt is. Psi of xt is nothing but exponential I p dot x by h bar minus I e t by h bar. So this immediately tells us that if we compare this expression with our general form of psi, which we have written here, then our rho in this free particle case will be 1, rho will be 1, and S of xt will be p dot x minus et, because this factor S comes with a prefactor of I by h slash in the exponential, which is already present. So therefore from these expressions it is very easy to check that if we calculate the gradient of S, it is simply going to give us P. And if we calculate del S del T, then it is going to give us minus E. So this is very important observation. We will be requiring these observations, and this is actually motivating us towards this semi-classical approximation scheme. Why? Because we see that in a more general scenario, I recall my J is given by rho times gradient of S divided by M. That's what we have just seen. So J is equal to rho times gradient of S by M. We can now see that there is something more to the wave function than the fact that just mod psi square is the probability density. What is that more part? The more part is that this gradient of the phase S contains a vital information. The gradient of the phase of the wave function, which is denoted by S, contains a vital piece of information. We can clearly see from this expression that the spatial variation of the phase of the wave function actually characterizes the probability flux. The stronger the phase variation, the more intense is the flux. And also I have just said that therefore the direction of J at some point x has to be seen to be normal to the surface of constant S. That is the meaning of gradient of S. So we have gathered few very important and interesting information from this thing. Let us also make sure that when we write down that this gradient of S divided by M, it is very easy to call this as some kind of velocity simply because we had written here that J is equal to rho times V by analogy with fluid dynamics. Now, therefore, if rho is already sitting, my V should be delta S by M. So this gradient of S by M, therefore, is my V, and the continuity equation in this case can be written as del rho del T plus divergence of rho times this velocity should be equal to 0. Just as what happens in the fluid dynamics case, because this is what we have seen, like del rho del T plus divergence of J. If we calculate, we know what our J is. So this is nothing but del rho del T plus divergence of rho V. Whatever V we have seen here is gradient of S by M. However, there is a caution that I want to mention at this stage, that this interpretation is too literal of J as rho times the velocity defined at every point in space, because that means that a simultaneous precision measurement of position and velocity is possible, which is not possible indeed in quantum mechanics, which violates the uncertainty principle. I will end this class just by mentioning another thing, is that we have just seen that there is an analogy between P and gradient of this function S. So if I now look down at the classical equation which we wrote, that P square by 2m is equal to E minus V of x, which gives us the kinetic energy. Here we can write this as 1 by 2m gradient of s squared, then plus v of x minus e, but e we have just now seen that del s del t with a minus sign. So this will be plus del s del t, which is equal to 0. Can you identify this equation? You must have encountered this in classical mechanics course. This is basically nothing but your Hamilton-Jacobi equation, where s xt stood for the Hamilton's principal function, if you remember, and therefore we can safely say at this stage that there is some kind of hint at this semi-classical approximation or semi-classical approach. At some limit of h going to 0, there is some transition between classical and quantum mechanical quantities. We will see, we will look at it more carefully. This is just a heuristic approach, I would say. I will try to derive this in a more straightforward way and critical way. But this is just to give you some idea that why the name semi-classical approximation is indeed required.